So we'll look at some integration tricks and what happens when you transform the functions that you're integrating in this video. So firstly, let's look at all these functions here. You can tell me some of their names or equations if you want to, have a think about it, but this one is y equals x, clearly. This is sine of x, this is x cubed. This one I'd be surprised if anyone worked out, but it's this apparently. And now think about what's interesting about all these, or four of these functions, particularly as it pertains to integration. What's quite interesting about them is if you just choose a value to integrate from, like here, and then choose that same negative value, if you were to integrate over this band here, you would get 0, because this area would cancel with this one. And it's the same here. If you were to choose the value here and the same negative one here, it would cancel, and likewise for all of these, like they would all cancel, and you get 0. These are called odd functions, and they have this really nice property that the integral of an odd function between some a and minus a is just 0, and so you never need to bother integrating the function itself. You just say, if you see the setup and you spot that the graph is symmetrical in this way, that it's just 0, and you don't do it. Like I said, these are called odd functions. You can tell that they're called odd functions because all the powers, x to the power 1, 7, 3, 1, 3, all the powers in the x's are odd. And you might think that this one is an exception here. I think I've put the definition down first. Yeah, the definition is this. So for some f of x, if x is 2, f of x is here, is equal to, if you input the negative x instead, then the function is just the same thing but negative. So that's what that's saying. This is also an odd function, of course, because you can write sine in case you've done some further reading. This is the Taylor series, and it just has odd powers, so it's also an odd function. This is just a really nice trick. So as soon as you spot a graph like this, or if you sketch a graph like this, which you're often going to do in Mirror, for instance, if you just spot a graph that does this or has odd powers like this, you can just say that this is just 0. You don't have to do the work. Okay, corresponding to that are also some other functions which behave a little bit differently and are instead completely symmetrical around the y-axis. And so again, if you think about integrating these two things, so this is x squared, this is cos of x, if you think about integrating these things between some a value and some negative a value, these don't work quite as nicely, but they do still have a nice trick, which is just that you can integrate this side and just times it by 2. Right? And this is quite nice because it means that you don't have to substitute in two values to your integral, because when you substitute in 0, you do have to substitute in 0, but it's usually really easy, right? So these are called even functions, and this is the definition where f of x is just the same as f of minus x, so it goes to the same place. The cos of x you can write like this, and therefore, again, you've got even powers in here, which is quite cool. That's why they're called even and odd functions. But again, if you spotted this kind of thing, this will just be equal, because they're all even powers, is equal to 2 lots between 2/3 and 0. And putting in 0 when to integrate this is going to be a bit easier than putting in minus 2/3. So that's quite a nice trick, but it's not as nice as the odd functions, which do just work immediately. So what about transformations then? So let's pretend that we know that the integral of f of x between a and b is some value x. What can we say about the integral of f of x plus c between those two values? Okay, let's just sketch. It doesn't matter what the sketch looks like, right? Just sketch some random function and say between a and b, you've got the area being x above the x-axis, of course. Now, what happens when you move the function up by some amount c? Well, the function moves up like this, and you're still integrating between a and b. And so what happens is you can say, well, let's just draw x, that area x, into here and cut it off somewhere. And you've still got the area x, but you've got this area as well. And this area is very easy to work out, because like this length here is the same as this one was here. So we can say that this length here is just c, because that's the amount that you've moved it up. Right, that's the amount that you moved the graph up by. And of course, this instance is just b minus a. And so the area, or the integral here, without actually integrating, is just going to be x plus c times b minus a, right? X, the original integral, plus this rectangle that you just made. And you can apply the same kind of logic to when you flip a function over. So for example, again, drawing this very quickly, the function is x. If you flip the graph over in the x-axis, which is what this is, the integral is just going to be negative x, right? And likewise, if you put a 2 in front of the f of x, the integral just doubles. If you put a 3 in front of it, it just triples. And so putting transformations in front or outside of the f of x thing alone is really straightforward, right? The integral always changes nicely. You just either times it by 2 if there's a 2 there, you times it by minus 1 if there's a minus 1 there. If there's a plus something on the end, you do this rectangle thing, but that's not too much work. It still works out. What's slightly more complicated is when you change the function inside the bracket. So when you either move it left or right, or squash it towards the y-axis if you've got 2 here, like that makes it slightly more complicated. So let's just discuss this really quickly. So again, we have this integral that we know the value of. Now here, What can we say about the function being moved one to the right between those two same limits? Well, we can say almost nothing. If you've moved the function one place to the right, and you keep a and b where they are, you don't know anything about this area, because you didn't know anything about this area here, like the one to the left from this original picture. So you actually can't say anything about this. That's kind of interesting in its own right. And likewise here, if you flip the graph in the y-axis, which is what this is, again, you have this integral. If you flip this in the y-axis to get this, but keep a and b the same, you can't say anything about this integral either, because, again, you didn't know anything information about this integral over here. Again, if you haven't been given any other information about the function. But what you can say, and this is kind of interesting, is what if you had this kind of setup? What if you had that the integral of f of x between a and b was definitely this, and the integral of the function moved one place to the right was that same thing between two different limits, big A and big B? What could you say about a, b, big A and big B? Could you say anything? Well, okay, the area is still x here. We've seen this a few times. We move it one place to the right, and apparently the integral between a and b is still this same answer of x. So what we could say is okay, well, a and b have also been shifted one place to the right. And so big A is just a plus 1, just moving it one place along, and big B is b plus 1. We could say that. However, this is a sufficient condition, but it's not necessary. It would be sufficient because if we did this, then the integral would definitely be x. But, I mean, we can just make a partition where the area underneath this graph just happens to be whatever number this is. Like over here, for instance. Let's say that this smaller sliver here was just x again, and I could just have a and b be whatever I wanted them to be. So it's sufficient to say that you could move a and b over by one place to get the same answer, but it's not necessary. You could do a wild number of other things. And it's exactly the same thing for the other transformations within here, right? So again, if you say this integral is x, and the integral flipped in the y-axis also has the answer of x, what could you say about a and b? Well, you could say that you've also flipped a and b, right? You've also, instead of using like 3 and 5, you're using -3 and -5. That's what you could say. That would be sufficient, but it's not necessary, right? Again, you could just partition it anywhere you wanted just to get an answer of x, and you could do that. So this is kind of interesting. I don't think Tamura has asked too much about this. There's not a question I can recall. It's definitely asked about this before. I just did a question in the integration video that I uploaded earlier today that used this concept, but that whole sufficient necessary thing hasn't actually asked about it, but it definitely sounds like that kind of thing they could ask about. So that's kind of interesting. Just in case I've made a wildly good prediction for 2 days' time, and I would feel like an immense god. But anyway, thank you for watching, and I'll see you next time.